Hello, my dear students. Once again, I welcome you all to KLS Gokte PU College of Commerce and Science, Belgavi. This is our lecture number 6 on a topic structure of atom. And myself, Mr. Akash Vasan Nesarkar, lecturer in chemistry, Department of Chemistry. Let us see the contents of today's class. The first, we will study the limitations of Bose theory. The second, the hydrogen spectrum. Third one, de Broglie equation. Fourth, Heisenberg uncertainty principle. Fifth, Schrödinger wave equation. Sixth, quantum numbers. 7, shape of orbital. And 8, nodal planes. We'll try to cover the maximum points in today's class. So let us start without wasting the time. The Bohr atomic model or its limitations. As we have discussed in the last class, the postulates of Bohr's atomic model. We know that Bohr model is applicable to only one electron system, and that was the first limitation of Bohr's theory. Let us see one by one. The first one, Bohr theory was very successful in predicting and accounting the energies of line spectrum of hydrogen, that is one electron system, could not explain the presence of multiple spectral lines. Means the Bohr theory is applicable to those atoms which contain only one electron system. For example, hydrogen, He+, etc. And if the atom is having more than one electron, then it could not explain the Bohr theory. It could not be explained by the Bohr theory. So Bohr theory is applicable to only one electron system. Second point, it could not explain the splitting of spectral lines in a magnetic field and electric field. Means how the spectral lines get splitted when we subject the magnetic field and the electric field, it cannot be explained by the Bohr's atomic theory. Third one, unable to explain the dual nature of matter as explained on the basis of de Broglie concept. So the Bohr failed to explain that dual nature of matter as it is explained by the de Broglie concept. The fourth one, it also could not explain the uncertainty principle, that is Heisenberg uncertainty principle. And fifth one, no conclusion was given for the concept of quantization of energy, how the energy is quantized. So no proof is given by the Bohr theory. Okay, so these are the limitations of Bohr's atomic model, you have to remember. Next, hydrogen spectrum. So in the last class we have studied about the spectrum, that is emission spectrum, adsorption spectrum, continuous spectrum and line spectrum. So line spectrum is very important in order to understand the hydrogen spectrum. So what is a hydrogen spectrum? First of all, see, when the hydrogen is subjected to electrical discharge in a gas and discharge tube, the rose color light is emitted, and when that rose color light is passed through the prism, it gives a different radiation which bend at a different angles, and those are arranged in an increasing order. And when these radiations are fall on a photographic film, we get a series of straight lines, and those series of straight lines is called hydrogen spectrum. Are you getting? So we'll get the series of spectrum in case of hydrogen spectrum, and those are fall on a photographic film at a different angle. Okay, so series of lines, that is a straight line we are getting on the film, and those lines are called as a hydrogen spectrum. And it is possible only when the electrons fall from the higher energy orbital to the lower energy orbital, then only it is possible to form the line spectrum. Next, so hydrogen spectrum. So how many lines we will get in a hydrogen spectrum? 6 lines we will get. Maximum we consider only 5 lines, okay, in your syllabus. So what happens when electron fall back from higher energy level to first energy level? When the electron fall from higher energy level to the first energy level, ultraviolet radiations are produced. The ultraviolet radiations are produced which cause Lyman series. So that is called as a Lyman series. So Lyman series is nothing but one, when electron fall from higher energy orbital to the first lower energy orbital, that is higher energy orbital to the first lower energy orbital, it is called as a Lyman series. So here n1 is equal to 1 and n2 is equal to 2. So these are the transition will take place in Lyman series. It may be 2, 3, 4 and so on. Okay, so higher energy means it may be 2, 3, 4 and so on. So remember that when electron fall from higher energy level to the first energy level, then it gives Lyman series and it produce ultraviolet radiations or ultraviolet region. It fall in a ultraviolet region. Next, Balmer series. When electron fall back from higher energy level, so when electron fall back from higher energy level, so these are higher energy level to the second energy level, then it produce visible region. It produce visible region. It fall in a visible region, and that series is called Balmer series. That series is called Balmer series, where n1 is equal to 2 and n2 is equal to 2, 3, so on up to infinity. So here the n1 is equal to 2, that is second energy level, not a 1. Okay, so such type of series is called Balmer series. Such type of series is called Balmer series. Next one, the Paskin series. When electron fall back from higher energy level to the third energy level, then it gives Paskin series and it produce infrared region. It produce infrared region. So here n1 is equal to 3 and n2 is equal to 4, 5, 6 and so on. Next one, bracket series. When electron fall back from higher energy orbital to the fourth energy orbital, then it gives bracket series and it produce infrared region. Here n1 is equal to 4 and n2 is equal to 5, 6, 7, 8 and so on. Next one, p fund series. So this is also important. When electron fall back from higher energy level to the fifth energy level, then it produce infrared region, and such type of series is called p fund series, where n1 is equal to 5 and n2 is equal to 6, 7, 8 and so on. And last one, Hampray series. When electron fall back from higher energy level to the sixth energy level, then it gives Hampray radius and it produce far infrared region. So these are the spectral lines of a hydrogen atom which contains only one electron system. As I said that it gives a series of spectral lines at a different angle, and those spectral lines are called as a hydrogen spectrum. So when it fall from higher energy level to first, it is Lyman. When it fall to higher energy to second, then it is Balmer. When it fall from higher energy to third, then it is Pascal. Fourth, bracket, and fifth, p fund. So these are the spectral lines or spectral series of a hydrogen atom. So I hope you understood this. Next, de Broglie equation. So de Broglie equation speak about the duality character of electron. Okay, so we know that wave particle duality, right? The theory of wave particle duality was developed by Louis Victor de Broglie. Who developed? It is developed by Louis Victor de Broglie. He proposed that moving particle have wave as well as particle property. जो भी moving particle है, so that is having the two property, wave and particle nature. The wave associated with the particle in motion is called matter wave. The wave associated with the particle motion is called matter wave. So if subatomic particle like electron can also have both momentum and wavelength, as we know that it is having the momentum and wavelength. So de Broglie, with this analogy, he gave the following relation between the wavelength and the momentum, for a moving particle, and that is lambda is equal to h upon m into v, where m is mass of the particle V is velocity of the particle, and the product of mass of the particle and velocity of the particle is P, that is called momentum, and H is a Planck's constant and lambda is a wavelength. So this is the de Broglie equation. So the de Broglie equation suggests that the wavelength of any particle is inversely proportional to the momentum. The wavelength of any particle is inversely proportional to what? Momentum. That is lambda is equal to 1 upon m into v, where m upon v is equal to nothing but p. That is a momentum. So it suggests that wavelength of any particle is inversely proportional to its mass of the particle and the velocity of the particle. Therefore, wavelength of a particle having large mass are too small to measure and recognize. Therefore, only particles which have very small mass can only have observable wavelength. So you have to remember this equation, which is important while solving the problems. Lambda is equal to h upon mv. So this equation is called de Broglie equation, where h is what? Planck's constant, whose value is given here 6.626 into 10 raised to minus 34 joules, and m is the mass of the particle, v is the velocity of the particle. Are you getting? So this is the de Broglie equation. We are not going to see the derivation at all. Next one, Heisenberg uncertainty principle. This is very important thing. This is very important concept. Heisenberg uncertainty. Uncertainty means uncertainties. Okay. So Werner Heisenberg, he is a German physicist, stated the uncertainty principle, which is a consequence of a dual behavior of subatomic particles and a radiation. The uncertainty principle is certainly one of the most famous and important aspects of quantum mechanics. The Heisenberg uncertainty principle states that it is impossible to specify at a given moment both the position and the momentum of an electron. Nothing but simultaneously determination of exact position and momentum of electron is not possible. So we cannot determine the exact position and the momentum of an electron. We cannot determine the exact position and momentum of an electron. So that is called as a Heisenberg uncertainty principle. It is uncertain. We cannot determine the exact position and movement of an electron when it is revolving around the nucleus, and that is given by the scientist Werner Heisenberg, and therefore it is called as a Heisenberg uncertainty principle. It is uncertain. We cannot get the exact position of an electron while it is revolving around the nucleus. Also we cannot get the momentum, that is velocity of an electron. As we know that electrons are falling from higher energy level to the lower energy level. Sometimes they shift from a higher energy level to the second energy level. So it is impossible to specify or determine the exact position and the movement of the electron when it is revolving around the nucleus, and that is uncertain, and therefore it is called as a Heisenberg uncertainty principle, and it can be given by the equation delta x into delta p is greater than equal to h upon 4 pi, where delta x is uncertainty in the position of the particle and delta p is uncertainty in the momentum of the particle. Okay, so delta x into delta v is uncertainty product. So in terms of uncertainty in energy, delta E and uncertainty in time delta t, this principle is written as delta E into delta t is greater than equal to h upon 4 phi. So this equation is Heisenberg uncertainty principle, this one. You have to remember this, where delta x is uncertainty in position, delta p uncertainty in the movement of the particle, h is always, you know that it is a Planck's constant, okay, and upon 4 pi. So this is Heisenberg uncertainty principle. It states that it is impossible to determine the exact position of the electron and momentum of the electron. Next, Schrödinger wave equation. When the electron is described in a three-dimensional wave in the electric field of a positively charged nucleus, we get the Schrödinger wave equation, and it is given like this. So this is our Schrödinger wave equation. Okay, and with this Schrodinger wave equation, we are having the four quantum numbers. The solution of Schrodinger wave equation provides a set of numbers called quantum numbers. And these quantum numbers help us to know the shape of the orbital, energy of the orbital, and many things. Okay, how many electrons are present in the orbital we can determine by knowing the quantum numbers only. Okay, so we are having the four quantum numbers. First one, the principal quantum number. The first one is the principal quantum number denoted by the symbol n. It determines the average distance between the electron and the nucleus. Means it denotes the size of the atom. We know that if it determines the average distance between the electron and the nucleus, then it determines what size of the atom. Also, it determines the energy of the electron and in an orbiter where the electron is present. Also, it determines the energy of the electron in an orbit where the electron is present. No energy cell in atoms is known as an element possesses more than 32 electrons. It gives the information about the orbital as well, K, L, M, N. So it gives the information of orbital, K, L, M, N. It gives the energy of the orbital, and it also determines the size of an atom. And fourth one, the maximum number of electron in an orbit represented by this quantum number is 2n square. It is represented by the quantum number 2n square. So we can calculate the number of electrons present in an orbit by using the formula 2n square. Okay, fine. Next, the second quantum number is azimuthal quantum number, which is denoted by the symbol small l, and it is given by scientist Summerfield. It determines the number of subshell. It determines the number of subshell or sublevels to which the electron belongs and about the shape of the subshell. So it gives the number of subshells present in an atom. Okay, if L is equal to 0, okay, then the orbital is s. If L is equal to 1, then the orbital is p. Okay, are you getting? Okay, fine. It also expresses the energy of subshell, that is s, p, d and f. So f orbital is having the higher energy compared to that of d, p and s orbital. So it also expresses the energy of subshells in an increasing order. We have here you have given the increasing order. So f is having the highest energy. Next, the value of L is equal to 0 to n minus 1 always, where n is the number of principal shell, represent the orbital angular momentum, which equal to h upon 2 pi square root of L into L plus 1. So it is equal to the orbital angular moment, that is h upon 2 pi and square root of L into L plus 1. Next one, the maximum number of electrons in the subshell. So we can also calculate the number of electron in a subshell by using the formula 2 into 2L plus 1, that is 4L plus 2. So we can calculate the number of electron present in the subshell, that is 4L plus 2, by using this formula. Next one, magnetic quantum number. It gives the number of permitted orientation of subshell. The value of m varies from minus L to plus L through 0. It tells about the splitting of fractal lines in a magnetic field, that is, the quantum number proves the Zeeman effect. For a given value of L, the total value of m is equal to 2L plus. So for a given value of L, the total value of m is equal to 2L plus 1. For a given value of n, the total value of m is equal to n square. So magnetic quantum number gives the orientation of the subshell. Orientation of the subshell. So m can have minus 3, minus 2, minus 1, 0 or plus 1, plus 2. So these are the possible values can be drawn. For example, if L is equal to 1, okay, so m can have the value minus 1, 0, plus 1. So m can have the value minus 1, 0, plus 1. If L is equal to 2, so m can have the value minus 2, minus 1, 0, plus 1, plus 2. So these are the values are possible. So it gives the possible orientation of the subshell. Next one, spin quantum number. The value of S is plus half and minus half, which signifies the spin or rotation of direction of an electron on its axis during the momentum. So it gives the direction of the electron around the nucleus, whether it is rotating clockwise or it is rotating anti-clockwise direction. So this can be given by the spin quantum number. The spin may be clockwise or anti-clockwise. It represents the value of spin angular momentum is equal to h upon 2 pi square root of s into s plus 1, and the maximum spin of an atom S is equal to half into number of unpaired of electron. So we can calculate the maximum spin of an atom by using this formula. So these are the four quantum numbers which are really important for the final examination. Okay, so principal quantum number determines the size of the atom. It also determines the energy of the atom, and shell, it gives information about the shell. Next, azimuthal quantum number, it determines the number of subshell, that is px, py, pz, how many subshells are there. Okay, then magnetic quantum number, it gives the orientation of the orbital. Okay, it gives the orientation of the subshell from minus L to plus L. Okay, as I said that if L is equal to 1, then M can have the value minus 1, 0, plus 1. And spin quantum number, it gives the information about the direction of orientation of electron, whether it is rotating clockwise or it is rotating anti-clockwise. So this information is given by the spin quantum number. So we'll stop here. The further things we will discuss in a next class. Thank you.